in calculus, you spend most of your time studying functions f, sending a number x to a new number denoted f of x. And these functions are given by all sorts of formulas. It could be a polynomial formula. F of x could be 2x squared plus 3x minus 5, or it could be a trigonometric function, or it could be a function involving exponentials, logarithm, etc. So in calculus you encounter all sorts of functions, and they can become easily more and more complicated. And but then there are tools for studying them, for drawing their graphs, finding extrema, minima, maxima, etc. You learn about the derivative, to study whether the function is increasing, decreasing, etc. So functions, well, are central in mathematics. But in this course in linear algebra, so far we have not studied function. We've studied what I would call mathematical objects that are kind of fixed. We've studied vectors, matrices. We've seen how to use these to solve system of equations. But we have not studied functions yet. So, well, you're mostly used to functions that send number to number, all right, as in calculus. But one can talk more generally about a function between two sets, whatever those sets are. So in this more general context, a function would tell you how to assign to an object of the first set some object of the second set. So, and it could be given by some formula. So I'm not going to review this general notion of function, but reminding you of that notion because then one can ask, so in linear algebra, well, we're not really looking at numbers, we're looking at vectors, at sets of vectors like Rn and Rm. So is there some good notion of function between these sets of vectors? And the answer is yes. Such functions are called linear transformations, and they have a certain number of specific properties. So this is a very central concept to linear algebra, this concept of linear transformation. So this is what we're going to study now. So linear, right? So that's the first point I wanted to make, is that yeah, these linear transformations. So written like this: linear transformations are the important functions in linear algebra. And well, first they can be defined using a couple of axioms. Okay, these are presented in the current learning activity, so I will not recall them now. But it can also be given just by matrices. So, well, first maybe I should go back and look at the simplest case. So, okay, so if you have a linear transformation, we usually use the letter T to denote it. Right? I mean, I could use F for function, but because transformation is a more standard terminology, so I will use transformation. So T, your transformation will send some vector in Rn to some vector in Rm. Right, so in calculus, maybe just to make the analogy with the notation calculus, in calculus you can have a function f that takes a number r and produces a new number r. Okay, and f of x will be given by some formula. So maybe f of x will be, no, I'm not going to write any specific formula. You've seen plenty in calculus. Okay, so, well, one can look at the simplest case. So we can take n and m to be equal to 1. Here, so I can take m to be 1 and n to be 1. And one can ask about linear transformations, T from the real numbers to the real numbers. I mean, one can view numbers as as vectors of size 1 by 1. So, I mean, usually in this course, we looked at vectors that have size at least 2 by 1, which have at least 2 components. Okay, but one extreme case is just when a vector has just one component, it's just one number. So it turns out that in this case, all the linear transformations are given by the following simple formula: T of x equals a times x. Okay, where a is some fixed, so here a will be some fixed real number. Okay, and I'm using x for an arbitrary real number. So it turns out that in this specific case, the linear transformations are the simplest function you can find. T of x equals ax, or if you want, f of x equals ax. Okay, and the graph of this of such a function is just a line that passes through the origin. So these functions are actually not very interesting from the point of view of calculus. And for linear algebra, well, this is also a bit too simple. But what we can do, get something more interesting, also a bit more complicated, is to look at Rn and Rm, where these will take values bigger than 1. So we can look at linear transformations from R2 to R2, from the plane to itself, from R3 to R3, or from R2 to R3, even from R5 to R7, etc. So we'll study, right? So we'll see how to study these. The good thing is that this result here, that in the case when you just have a linear transformation from R to R, that T is given by the simple formula. Actually, this generalizes to any n and m. So actually, in general, a linear transformation will be given by the following formula: T of v, T applied to a vector v. This will just be some fixed matrix A applied to the vector v, where A is going to be an m by n matrix. It is an m by n matrix, which is fixed. So it's an n by n matrix, which is fixed. Okay, v can vary. V can be any vector in Rn. A times v will be a vector in Rm. Okay, and T is given by this rather simple formula. So, right. So we'll see why any linear transformation is given by such a formula, and this means that to study T, well, you can study just the matrix A, which is something quite concrete, right? You can, you can apply row operations to A. You can row reduce A. And this will give you information about the linear transformation T. Okay, so in many ways, actually, linear transformations are simpler than the functions you see in calculus. Okay, so of course in calculus, and first year calculus course, you look only at functions of one variable x. You have one number x and you have a number f of x. Okay, but the formula for f of x can be quite complicated. Its graph can be quite complicated, etc. These linear transformations are given by much simpler formulas, just a matrix times a vector. But of course, the vector can have, many entries, and this does create a bit of complications. One thing is that one cannot talk about, cannot picture the graph of a linear transformation. So there will be a way to define what is the graph of a linear transformation, but it will sit in higher dimensional space and you cannot visualize it. Right? In calculus, one good thing you learn to do to study a function is to learn to draw its graph. And if you see the graph, then you can tell things about the functions. Unfortunately, in linear algebra, we cannot do that, but still we have a concrete, matrix A, and we can use that to study the linear transformation. Okay, although T is not necessarily given right away by a matrix A. Okay, it can be sometimes given a slightly different way, but there's always a way to find a matrix A. All right, so now just I just want to look at some examples of linear transformations, okay? And the next video, we'll see how to check if a function is a linear transformation or not. But now I just want to look at some examples. So you already know some examples besides t of x equals ax. So I want to look at the case when n and m are equal to 2, right? So because there we can picture something if m and n are equal to 2, right? So we're looking at linear transformations from R2 to R2. So there's right? So here, so we can visualize something. And what are some examples? Right? I mean, okay, you could take A to be a 2 by 2 matrix, but I want examples that we can see. So one of them is actually given by rotations. So I drew a circle here, right? So you could imagine this is the unit circle, okay? The blue vectors are the standard unit vectors, 1, 0, and 0, 1. Okay, and you can decide to, right, and so the circle is centered at the origin, okay, and you can rotate the whole plane, right, so by some angle, okay, so usually often the angle is denoted theta. Well, we've used theta before to denote the angle between two vectors. So theta, this Greek letter, is a standard letter for denoting angles. So sorry about this. Right, so I can write it here, although I think I'd use this marker, slightly different red. Okay, so we can take the plane, fix the origin, and then rotate the whole plane by an angle of theta here. So if we do that, then there's the vector 1, 0, right? So we'll be rotated and we'll get one of these, we'll get this first red vector, okay? If we take the vector 0, 1 and rotate it also by the same angle, theta, okay, then we'll get the second red vector. And we can rotate any vector in the plane, any point on the plane, around the origin, always by the same angle. Okay, so rotation of the plane is an example of a linear transformation. Okay, so this is not entirely clear. If you look at the axiomatic definition of a linear transformation, it's not so clear that that the rotation is linear, but that's indeed the case. Okay, and there's a way to get at matrix A. But this is the subject of the next learning activities. I won't talk about it now. The matrix A will have some entries given by cosine of theta and sine of theta. Okay, so we'll see this a bit later. The main point here is just to learn that rotation in the plane is an example of a linear transformation from R2 to R2. Okay, other examples are reflection with respect to a line. Okay, so we'll come back also to this in some other video. Okay, so when you reflect with respect to some line, you do get a linear transformation. Maybe I can actually draw a little something here. All right, let's see if I can move this a bit. All right, so if I draw some line here. Right, so what will be some what's a reflection with respect to a line? Right, so how do you reflect with respect to a line? Well, if you right, so in this case, okay, well, maybe I could do reflection with respect to the x-axis. That will be the simplest thing. The origin is already there. Okay, so let me extend the x-axis like this. Okay, so reflection with respect to the x-axis would, for instance, take a point here. Okay, and then you reflect it, so you're going to look at the point that's across the x-axis and locate it at the same distance. Okay, so let's see, I'm Right, so this should be, okay, it says 90 degrees. So I should find the point that's on the other side of the x-axis, but about the same distance. Okay, so the question is, was my horizontal axis? Yeah, it was 0. Okay, I was under the impression this was not quite right. Okay, well, I have to follow what this says and not my eyes. Okay, so so I have to find the, right, so this point here, right, so this is the point that's obtained by reflecting this point with respect to the x-axis. Well, here I'm just drawing the point. You can imagine that this is represented by some position vector. Okay, if I take the position vector and apply reflection with respect to the horizontal axis, then this is what I get, right? So the reflection will send this point to this one and vice versa, right? So this is what reflection is with respect to the x-axis. So this is also an example of a linear transformation. Reflection with respect to any line actually in the plane is also a linear transformation. Okay, and I hope to come back to this example a bit later in some other video. All right. So this is right in R2. One can also look at rotations in R3. So rotations in R3 are also linear transformations. So what's a rotation in R3, you may ask? Well, the main example would be the example of the Earth rotating on its axis like this. Right? So there's some axis of rotation going through the North Pole and the South Pole. This is fixed. Right? If you're on the axis of rotation, you actually don't rotate. Okay, and the Earth rotates around this axis. All right, so right, so this is what the rotation in R3 is. It's not that, I mean, if you're in the plane, the origin, you have rotation around the origin doesn't move, but everything else is going to rotate around it. In three-dimensional space, this is not true anymore that only the origin is fixed and everything else rotates. There's always an axis of rotation, so a line going through the origin that does not rotate at all, that is fixed, okay? But everything else is going to rotate around it. And the way to understand these axis of rotation is actually by looking at the plane that is orthogonal. So the way to understand the rotations in R3 is by looking at a plane which is orthogonal to the axis of rotation. Okay, so to do that, got a little props here, so let me just enlarge a bit this, enlarge myself a little bit, okay, to cover this. And okay, so this prop looks a bit ridiculous. Usually when I teach in class, I have something a bit better. But that thing is in my office, okay? So I had to get something at home. So, all right, so if we have, so imagine that this stick, so this represents the axis of rotation, okay? And I've got the two vectors here, okay? So actually now that, because you see things a bit differently, I'm thinking that maybe I should actually put one tip on the other side, so things look a bit like what you're used to. So, right, so, all right, so, just a second. All right, okay, so we got the axis of rotation is the stick, and I use this is going to represent a plane that is orthogonal to the axis of rotation. I just want to see what happens on that plane, okay, so had some paper plates, so that's what I use. In any case, I cannot have a full plane, I need part of a plane, okay, so this is what I found at home, and I think this will serve its purpose, so it looks a bit ridiculous, but you'll see what I mean. So let's look at the case first where, let's say, the axis of rotation is pointing towards you. Okay. Well, what I can do, right, so imagine it's fixed. I'm trying to maintain it's fixed. But I can still rotate the axis, and then it's the plane that rotates. Right? So let me try to give it like this. Okay, so the point is that when you have a rotation in R3, the axis of rotation is fixed, but if you take a plane that's perpendicular to it, on that plane, you get a standard two-dimensional rotation. Right? And you can see it, I drew two vectors. You can think that these vectors are the standard vectors, 0, 1, 1, 0. And as I rotate the axis of rotation, so I'm applying some rotation in R3, well, this plane is rotating on itself. Okay, so the rotation fixes the plane. I mean, it sends the plane to itself, but the vectors on the plane just gets rotated. Okay, so the point I want to make is that this kind of rotation in R3, it's actually just a rotation in R2 on a plane like this that is extended to R3 by fixing the axis of rotation. Okay, so but of course things get more complicated because the axis of rotation could have any sort of orientation. It could be oriented like this, for instance. Okay, and all right, but even then, even when it's like this, you see the axis is fixed, and all that rotates is, well, the plane that's perpendicular to it. Okay, so I mean the rotation sends the plane to itself, so you get the rotation of that plane. But all the vectors on the plane, they rotate by some angle. Okay, I could decide, well, the angle is theta, and the angle is, this is, rotation by theta. That's it. That's what it looks like. Okay, so, right, so this is how we can think of rotations in R3. Okay, well, first you think of the example of the Earth rotating onto itself. But if you want to understand better what is going on, you have to think about a plane that cuts the Earth at the equator. Okay, so the important thing is, right, is that plane, and see that there, what you get is just a standard rotation. Okay, so rotation in R3, you can start, you start with your standard rotation by some angle, and then you just move the axis of rotation, and then you fix it somewhere else. Okay. So rotation in R3 is determined by this, the axis rotation and the angle, okay? And it's also given by some matrix, which is not at all obvious. Maybe in some other video I'll tell you a little bit how to find that matrix. Okay, so this is another example of a linear transformation. Okay, and I want to still show you some more examples. So let me just make myself smaller again. Okay, and so there are some demo you can find on the internet. Let me lower this. Okay, to see what a linear transformation it can produce. So okay, let me start with this one actually. Okay, so some website where I can show you where I found this, so you can go to that URL if you want to play a bit with this. Okay, so we've got the matrix A for the transformation. So this is a transformation. I want to illustrate a linear transformation from R2 to R2 given by that matrix A. So 1, 1/2, 1/2, and 1. Okay, and so I'll play this little animation here. Okay, well, first I'll play it. I'll tell you what it does. Okay, so in that case, I mean, what is green? Okay, initially what is green is the unit square, the square that of side 1 with one corner at the origin. So if you apply, so the linear transformation can be applied to all of R2, so you can apply to that square, and you can ask what's the image of that square under your linear transformation? What do you get? Okay, and here, well, for that matrix, you see that it transformed that square onto this this rhombus, okay, with some diagonal along the line y equals x, okay, and also in this animation, this is done kind of progressively. So if you just have the linear transformation itself, well, yeah, it sends the square to this rhombus, like this. But here we have this little animation that shows how the square will move, progressively, how it will transform itself progressively from the unit square into this rhombus. Okay, so I mean, this could be done by take your matrix A, you introduce some parameter t denoting the time. Okay, so that initially when t is 0, the matrix A is just the identity matrix, and when t is 1, you get this matrix 1, 1 half, 1 half, 1. Okay, so you can play with this. So this is it's called end-to-end linear interpolation in this case, but there's some other option here. Right, so you can see this at the okay, I can see it here. So this is called the end-to-end. So you see the initial square, the end square, and all the images in between are what is called interpolated. Okay, to show progressively what is happening. But you can also get this rotation, scale rotation, and play this. Okay, and you see that what you get is first a rotation. Right, your square gets rotated, then it gets kind of stretched along the x-axis, and then it's rotated back, like this. And you get the same result in the end, okay? Well, it's because any linear transformation in R2 can be expressed as, first you do a rotation, then you kind of stretch your image. Essentially, in this case, the matrix A is just a diagonal matrix, and then you do a rotation again. Okay, it's not something that will be explained in this course, but the point is that most linear transformations, yeah, they are given, but well, all linear transformations can be obtained using rotation and this kind of stretching that you see here. Rotation, stretch, rotation. Okay, so this is what is happening in R2, and you can see it on this animation. You can change the matrix. At the top, I can set it to be 1, 3, negative 2, 4. Let's see what we get. What happens to the unit square, to that green square, when we apply this different transformation? We can play this. Okay, now we get something that's different. We get some parallelogram. Okay, and that looks like this. Okay. So one side gets stretched more than the other, okay, and also the square gets also rotated, okay. So you can play this a bit differently, okay. Rotation, stretch, and rotation again, or scale. The figure is scaled. So all right. So this is one way to visualize linear transformations. There are other applications. Like we can go to this one, for instance. It's kind of similar. You can play with the Mona Lisa. Here, so you can, you have the matrix M. Okay, instead of A, it's a notation that uses M. So you can change the entries A, B, C, D. So initially, it's the identity matrix. If you apply the identity matrix, you don't change your vectors. Nothing happens. Okay, but you can decide to change A, for instance. So if I increase A, I'm going to stretch Mona Lisa like this. If I give it negative value, I'm going to actually flip it on the other side, reflect it with respect to the y-axis. Okay. I could also do something with D. So I can stretch with D. Positively, I'm going to stretch it vertically. Well, that's a linear transformation. Okay. Or I could give D some, or I could shrink it. If I give D some positive value that's between 0 and 1, and if it takes negative value, then I'm going to actually reflect it, right? So there you go. Here you get some reflection with respect to the x-axis, which is what I was talking about? Well, reflection and stretching also, okay? So, and you can play with this. Well, okay, I'll put it back at, if I put it back at 1, right? You can ask, what if I modify B? Well, then you're going to kind of just stretch one side. You fix the base along the x-axis, but you just stretch the top, okay? So this is what happens when you change B. Okay, when you change C, well, you're going to stretch it vertically like this, just along one side, up or down. Okay, and then if you want, you can play with what happens. See what happens with all these values of A, B, C, and D. Okay, so this is the effect. Okay, if your linear transformation is given by that matrix M, you apply it to all of R2, and you see what happens, especially to that Mona Lisa. I mean, each pixel here has some position vector, and applying the transformation to that vector tells you where that pixel goes. Okay, so you get this, you'll get this image. Okay, so this is I found this on GeoGebra. Okay, so you can play with this if you want. One thing that can be proved about linear transformations is that they send lines to lines. Okay, maybe that might be a little exercise later on, or maybe I'll explain this in some other video. We'll see. But this is illustrated by here. So if you go to Desmos here, right, one can also play some two-dimensional linear transformations. Okay, one can choose the matrix. So here I have the matrix 1, 3, -2, 4, and I can play this. I'll play it like this. I'll show it to you. Okay, so you can see what is happening. So this is again some sort of interpolation. Okay, so if you apply your linear transformation to all of R2, well, you know, it will transform your vectors like this. Okay, and it would, in this case, the vector 0, 1 will be sent to this this kind of pink dotted vector here. Okay, and the vector the vector 1, 0 is sent to this pink vector here. The vector 0, 1 is sent to the dotted blue vector here. Okay. But here this is done kind of progressively also to show some nice animation. Okay. But what I want to illustrate here is that if you start with this, so I can go back here at the beginning. Right, we start with that grid, so all these lines. We can also apply the linear transformation to all those lines, right? It can be applied to any vector or point in R2, so we can apply it to all those lines. And when we do that, well, you can see what happens to the lines. They get, they can get rotated, things get stretched also, like the distances between the line can increase or decrease. You can see that also about the vectors, right? Initially, we start with these two vectors, 1, 0, and 0, 1, okay? And you'll see as we apply that linear transformation is actually going to stretch them so they become longer, but one of them becomes a lot longer than the others. Okay, but also all the lines becomes other lines. They get rotated. They get they get stretched also. Although if you take a line, you stretch it, you just get you get back the same line. So you don't really see that, right? You can stretch an individual vector. A line is already infinite, so stretching doesn't make much difference. Okay, so all right, so you can use this kind of applications to see what happens with linear transformation. Okay, so that's one way to visualize them. Of course, when you want to study them, you really need the matrix. That's the matrix that gives you the information. But I thought, it's nice to still to see a bit of geometry, see some pictures. I mean, that's one difficulty with teaching. Well, first with teaching math as compared to other sciences. right? If you study maybe biology or physics, you can maybe see a lot of nice and interesting pictures in your courses to illustrate some concepts. And math, that's not so much the case, right? In calculus, well, pictures you see are mostly graphs of functions. That's not that interesting. And in your algebra, it's even worse, right? What are the geometric objects we work with? The pictures we see are just lines and planes and vectors, so it's not, I know it's not that interesting. Here at least there's a little bit of animation, okay, so that's one reason why I thought I would show these to you, and try to convince you also that linear transformations are interesting, in particular if you are interested in working with graphics, 3D graphics for computers, for instance. Well, you need to know about linear transformations, right? Well, I just said rotations are linear transformations, so you need to learn this, okay? And right. So this is what is happening in higher dimensions. A bit harder to illustrate. Well, in R3, it might be possible to design similar demonstrations, but of course, in the higher dimension, it's not possible to picture things. Okay. So, but then again, as I said before, we've got algebra, so we can use algebra to understand what happens in higher dimensions.